So, dear students, let us continue moving charges and magnetism. In the last class, we discussed about an important concept, Ampere Circular Law, right? And this Ampere Circular Law will help us in getting the magnetic field value at a particular point around a wire in a simpler way, right? We got the expression for that in the last class. So now, uh, and before the discussion of Ampere Circular Law, we have discussed about the magnetic field produced by a current carrying coil or a loop of current carrying conductor, right? A single loop, if we have derived it actually, right? On the axis of the loop, at a point P, we obtained the expression for magnetic field, right? And now this is uh, when you have current flowing through a coil like this, okay, out of the board like this, then the magnetic field produced will be like this, right? This is the direction of magnetic field produced when you have the current in this way out of the board here and into the board here in the current carrying conductor in the circular shape. Okay, a current carrying conductor in circular shape can produce magnetic field in this direction given by right hand thumb rule again. Now this is an incomplete picture of the total magnetic field, okay? Because when we go for getting complete picture, the complete because if I ask, will there be any magnetic field here? Yes, there will be magnetic field here. Here, yes, 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 yes. Everywhere near this circular coil, there will be magnetic field present. So, let me give you the idea about the magnetic field at in the entire region surrounding the coil. Okay, because this is a simple length or simple line chosen on which we can get the magnetic field value and direction. But how does the magnetic field in around okay, all around the coil look like? Okay, when I draw the magnetic field for that, it would look somewhat like this. Okay. So this is how the magnetic field around the current carrying conductor look like. Okay, so here, because that is what we know, okay, in the beginning itself we have discussed about it. Okay, if I have current I flowing, and hence we'll have the magnetic field like this, okay, perpendicular to it. So this is the situation when we have a single turned coil, okay, a coil with single turn, only one turn. If I have a coil of say n turns, okay, n turns, let's say I start from this point and I make n turns of coil, okay, so many turns of them, then what is the magnetic field value and direction of magnetic field in the entire coil chosen. So extending the same idea, see, this is the pattern of magnetic field when I have single current carrying coil. If I have two of them, this part of magnetic field would stretch. See, these curves what we have here will start to become parallel lines as many parallel lines, see, as we add more and more coils. Following? So one coil is giving us the formation like this. Two coils, these curves will start to become little parallel to this line, the one in the center. If I add one more, three more like that, keep on adding them, then the magnetic field, okay, since all of these turns are contributing for the magnetic field, the pattern of magnetic field due to this kind of helix or this kind of coil is called is as shown in the diagram. Okay, because now what has happened is these curves starts to become parallel to each other, and hence they become completely parallel to each other inside the coil, and when they come out they take a loop again. Okay, like this we will study in detailly about magnetic field in the next chapter. Don't need to worry about the complete idea of magnetic field lines, magnetic field and all. In the next chapter we'll study that, but this is a small introduction which I needed to explain a particular shape of conductor which we are going to discuss now. Okay, so this is how the field lines would look like when we have a coil of n turns. If it's a coil of one turn, this is how it would look. Okay, so this is the basics foundation, and now we are going to build concept on these concepts. Okay. Okay, now when I say coil, the coil can be of any kind of metal chosen, and it can be either insulated or non-insulated. Okay, when I say coil of this kind, so if I make few specifications, okay, few conditions for this coil, this kind of n-turn coil, we can name that coil a particular term. Okay, so now I'll define a particular coil. Okay, a particular coil, which is an insulated copper wire. Okay, I'll take an insulated copper wire wound into or wound closely in the form of helix, in the form of helix. So this is a coil, regular coil, nothing else. The specification is a coil is nothing, coil will have the shape of a helix, right? Helix, you know that now, like this, that is what is helix. But here the conditions are the wire chosen should be made up of copper and they should be wound closely, okay, close to each other. And it should be the copper wire chosen should be insulated, which means it should have a coating of insulator or like rubber, right? If I have such a coil, such a helix, we name that helix as the solenoid. Okay, let me show you how exactly it looks like. Right, just visualize this. This is a regular copper wire. Okay, you can see this. This is pure copper, and this copper wire is insulated, right? So this is an insulated copper wire. Okay, what should I do with this? I should wound it closely in the form of helix. How do I wound it? I'll take a support like this, okay, and then I'll start wounding it like this. One turn, two turn, three turn, 4, 5, 6, so on. Just a minute. Yeah, this is how it looks like after wounding it. Okay, and they have not mentioned that it can have anything inside it or it should not. Okay, there's no specification about it, so I can, even if I keep the metal rod inside the wire, inside, what is this now? This is a insulated copper wire closely wound in the form of helix. What is this? This is a solenoid. This itself is a solenoid now, and there is no specification about any support. Okay, whether there should be something inside the solenoid or there should not be anything. Okay, so even when it stays inside the rod, it is a solenoid, or even if I take the solenoid out, even now this is a solenoid. Okay, so this is what is actually a solenoid. But in practical situations, what happens is we take small wire and wound it so close, okay, thin wire, and wound it so close for a lengthier for a lengthier length. So that's what makes a solenoid. Okay, yeah, this is also a solenoid, and this shape itself is helix, you know that well, right? But the condition for solenoid is it should be closed, the wire should be insulated, and it should be made up of copper. Why copper? Copper is a good conductor of electricity. That's why we choose copper for this. Okay, so this is what is a solenoid. Now visualizing solenoid pictorially, that looks somewhat like this. In a physical form, it looks like this. Okay, but when I take the view with the magnetic field, the solenoid would look somewhat like this. Okay, let this be the cross section, horizontal cross section of the solenoid, which means, say I take this solenoid, okay, take this solenoid, see, and cut it like this in the middle. Okay, if I cut it like this in the middle, it would look somewhat like this. I should not cut it actually. Okay, it's the cross sectional view. Then, okay, the wires would be coming like this, right? This is how the wires would look like. Now, I should connect one end of it to either positive or negative terminal. I must do that, right? So let me say I have connected one end of the wire to a positive terminal and the other to a negative terminal like this. Okay, right. So now, what about the direction of current flow here? The direction of current flow would be, since this is positive, it would be like this. Okay, and goes back and comes again here, okay, with the second turn. In the second turn, goes like this. This is how the current direction would be. So if I want to represent the current direction on one end and the other end of the solenoid, then I can make use of dot and cross. What should I put here to represent the direction of current? Dot or cross? It's a dot, right? Because the current is coming out of the board, somewhat like this, coming out of the board. Even here, it is coming out of the board. So this is what the diagram in the reference represent. These dots represent current direction. As such, they are coming out of the plane. And here, the same current is going into the board like this. Okay, the actual wires are like this. So it is cross, which can be used to represent direction of current in the bottom of the solenoid. Okay. So now I don't need these wires to represent the direction of current anymore. I can move ahead. Right. So, and as of this particular concept is concerned, we do not have, or you do not have a proper derivation for the magnetic field inside it, okay, for the board syllabus. Anyhow, I will be deriving the derivation now, but in fact, you do not have any derivation regarding solenoid and toroid, which is coming now. So don't need to worry about the derivation, but conceptually the derivation part is important. You can apply that conceptual understanding in various other situations of competitive exams. That's why. Okay, right. So then, if this is a situation, current like this coming out of the board and entering into the board like this, what should be the direction of magnetic field inside it? The magnetic field inside the solenoid looks somewhat like this, isn't it? Uniform magnetic field is set inside the solenoid. What is uniform magnetic field? You check the magnetic field here, same. So every point inside the solenoid will have the same magnetic field. Okay, that is what is uniform magnetic field set inside the solenoid. And now our intention is to get the value of that magnetic field, right? Let us work with that now. For that, I am going to choose, okay, there is no derivation part of it, I will be doing it faster, but the final expression is important, okay. Derivation is not asked for board examination, but even then I am doing it for the conceptual understanding. So, in order to derive or get the value of magnetic field inside this solenoid, I am going to make use of Amperian loop. Okay, I will consider an Amperian loop in the shape of a square this time, okay, or a rectangle is fine. A rectangle of rectangle. Let me name the rectangle as P, Q, R, and S. Okay, P, Q, R, S is the Amperian loop. To complete the loop, I can say P, Q, R, S, P. This is the loop that I have considered to get the value of magnetic field inside the solenoid. Before that, I should take few considerations for the given solenoid. Let the solenoid is of length or the Amperian loop chosen distance from S to R, that length be L. Okay, let L be the length of the chosen Amperian loop. Okay, yeah, don't need to worry about this. You'll get to know why they are not important. So it is L, which is the length of SR. Okay, that is chosen, and N, small n, be the number of turns. Okay, be the number of turns per unit length, which means the the number of turns that we have in the solenoid for 1 meter of solenoid, okay, ideally. So n is the number of turns per unit length. This is mathematically very significant. You should keep this in mind. Number of turns per unit length, which can be considered as uh, total number of turns in a length chosen L. Okay, so say you have so many number of turns here, n number of turns, 1, 2, 3, 4, and length is of certain value, capital L. Then number of turns per unit length is capital N by L. Okay, easy. So and let I be the current flowing through the wire. Okay, because whatever the current enters here will flow through each of these turns and hence comes back to the battery. So I is the current flowing through each turn of the solenoid. And now applying Ampere Circular Law to the loop. Ampere Circular Law says closed line integral of B dot dl is equal to mu naught I, right, total current enclosed by it. So now this B dot dl, when I take and apply it here, see, magnetic field inside the solenoid is constant, right? You take the magnetic field here, here, it is constant because it is uniform magnetic field. So I can take the part from P to Q, Q to R, R to S, S to P separately and apply the integration. So because see, B dot dl represent the loop starting from P, taking B dot dl, B dot dl, B dot dl, B dot dl for the entire loop. And now since magnetic field is uniform inside, I can take from P to Q as one entity of magnetic field. Okay, so that would look like B dot dl from P to P again. Okay, P to P can be written as integral of P to Q. Okay, from P to Q B dot dl once plus from Q to R, integral of Q to R B dot dl, okay, plus integral of R to S again B dot dl, and finally integral of S to P B dot dl. Okay. So now what is B dot dl? It is B dl cos theta, where theta is the angle between B and dl, right? So what is the angle between B and dl? dl is length, B is magnetic field. For the length PQ, when I take length PQ, dl starts from P, ends at Q. This entire length is dl. So this is the direction of dl. What is the direction of magnetic field? That itself is the direction of magnetic field, which is already set. So for P to Q, theta is 0 degree. Then let me come to Q to R. When I come to Q to R, the magnetic field is perpendicular, right? The length element is like this, Q to R, and the magnetic field is exactly perpendicular to it, which makes the angle between B and dl equal to 90 degrees. Right, following. There is no derivation, so I am not going with the actual steps. So, but you should understand it conceptually. So, let me come from R to S. When I come from R to S, here S, the angle cannot be 90 degree, but if you observe the magnetic field pattern which I wrote, the magnetic field exactly outside the solenoid, outside the solenoid in this region will be 0, because the magnetic field lines will go away from the center like this. So, at this region the magnetic field would be close to 0, okay, very close to 0, which means when I take it from R to S, magnetic field itself is 0, vanishes. So, here no magnetic field, no magnetic field, no magnetic field, no magnetic field. Here, yes, there is, because it is inside the solenoid. And you can find the magnetic field somewhere there. Yes, it is possible, but exactly above the solenoid, you cannot find any magnetic field. So, same way, when I take it from S to P, from here to here, once again, the angle is 270, okay, because this is dl and this is what is this? This is B. So, either 270 or 90. So, once again theta is 270 degree or 90 degree, okay, fine, that is fine. So, here B dl cos theta, which is B dl into cos 0, which becomes 1. So, it is from P to Q, B dl cos 0 is 1. I will not write that again, okay. So, all these terms vanishes to 0, because cos 90 is 0, 0, B itself is 0, so entire thing is 0. So, here also 0, 0, 0. So, rest of the terms vanishes. What will be left with is only the integral of B dl integrated from P to Q, that is it, okay, only from P to Q. And when I take the length from P to Q, from here to here, as you can see, the magnetic field is uniform. I have told you about it, right. Since the magnetic field is uniform, it will be a constant term when I move from point P to point Q. So, I can take that point outside, take that quantity B outside, and what will be left with inside is P to Q dl. Okay, it is going to be B into what is integral of dl, which means you just add all these lengths. What is that equal to? That's equal to L, right? Because it's a rectangle chosen. So, it is going to be simply BL, clear? Very easy. But this is the reduced form of integration that we should do, integral of B dot dl. But the Ampere circular law says this integral of B dot dl is equal to mu naught I. So, this BL becomes equal to mu naught I, right. So, now what we need is this value B, okay, the expression for B is what is important for us. So, finally, we are in the expression BL is equal to mu naught I, okay. Yeah, before that, see what is I here? I is the total current enclosed in the Amperian loop, right, which is this. So, if I have only one current or only one coil from here to here, then the current that I should consider is simply I. But now you observe carefully, we have 4 turns, particularly 1, 2, 3, 4 turns coming out. So, it is 4 times the current in each turn of the coil enclosed inside the Amperian loop, right. So, in general, since we have chosen N, capital N as the total number of turns inside the solenoid, okay, that makes, instead of simply I, this time I should put capital N I. Following why? Because Amperian loop, Amperial law, Ampere circular law says the line integral of B dot dl is equal to mu naught times the total current enclosed. If I have only one coil, that is simply I, that is fine. But now I have n number of turns carrying I amount of current. So, the total current enclosed is capital N into I, clear. So now if I send L to the other side, or that becomes B is equal to mu naught N by L I. What is N by L? Look at this. N by L is number of turns per unit length. Per unit length. So that makes the expression for magnetic field inside the solenoid is equal to mu naught N I, where N is the number of turns per unit length. I is the current flowing through each turn. All the turns will have I amount of current. So as I say, this derivation is not there for you as with the concern of board syllabus, but the concept you should be aware. The way how we make use of Ampere Circular Law and get the expression, that way has to be understood. Okay, it's very important. So this is about solenoid and the expression for magnetic field inside the solenoid, which means now mu naught Ni is the magnetic field inside the solenoid. Okay. So at this point, this point, this point, every point inside the solenoid, magnetic field is equal to mu naught Ni. Okay, inside. So there are few conditions or special kind of solenoids. When you have, when do we say a solenoid as a long solenoid or a lengthy solenoid? Very simple. When we have the length, the total length of the solenoid very much greater than the radius of the solenoid. Okay, just a minute. Let me bring that and show it to you. So this is somewhat like a regular solenoid. Okay, but at the same time, if you have one more solenoid of the same radius, okay, this is the radius of same radius, but with very large length, say the same solenoid like of this much length, say 1 meter itself. So in that situation, radius is very small, somewhat like half centimeter, but the length of the solenoid is 1 meter, 100 centimeter. So there, length is very much greater than radius. That kind of solenoids are called long solenoids. Okay, long solenoids, where the length of the solenoid is very much greater than the radius of the solenoid. And one more important kind of solenoid is, okay, this is long solenoid and the other is ideal solenoid. This ideal solenoid is something where is a solenoid with the length equal to 5 times the radius. Okay, so the length of the solenoid should be 5 times the radius of the solenoid. Say this radius is half centimeter. Okay, half centimeter. Then what should be the length of the solenoid in order that solenoid to be ideal? So it is half times 5 is 2.5. So the length of the solenoid must be 2.5 centimeter in order to make this solenoid ideal. Okay, so that's the condition for ideal solenoid, where length of the solenoid is 5 times the radius of it. Okay, rest everything is same. Clear with this? So this is everything about solenoid. And one more thing, important one is, what about the magnetic field at the end of the solenoid? Okay, because this is mu naught Ni is the magnetic field inside the solenoid, which means somewhere here inside the solenoid. Okay, even if I close it, this is how actual solenoid look like. When I take a point inside the solenoid here, that would be mu naught Ni. Okay, mu naught Ni. But if I take a point outside the solenoid or at one end of the solenoid, exactly here, this is a point which is at one end of the solenoid, either this or this. That would be exactly half of this. Okay, so magnetic field at one end, B end, that's how I'll write. Magnetic field at one end of the solenoid is equal to half of the magnetic field inside the solenoid. What is the magnetic field inside the solenoid? It is mu naught Ni. Half of it is mu naught Ni by 2. Okay, clear with this? So this is everything about solenoid, its special cases and different kind of solenoids. Okay, if you want, you can take this, or else, yeah, for the understanding purpose you take this, but you don't need to memorize this step by step, because it's not asked for board examination. Thank you. Okay, the next device that we are going to consider is very similar to, or at the next level, or the next version of solenoid I can call. Okay, it is called toroid. Okay, toroid is again which can have magnetic field inside it. Okay, it's a toroid is basically an helix. Okay, it's a solenoid. Okay, toroid is a solenoid bent into the shape of a ring. Okay, see, this is a solenoid bent into the shape of a ring, right? This itself is now toroid. That's it. Clear? Very simple. What is toroid? Toroid is a solenoid bent in the form of a ring. Okay, so this solenoid is bent like this. So if I draw the diagram of the toroid, that would look somewhat like this. Okay, this is the diagrammatical or pictorial representation of toroid. So now, yeah, you might be thinking, what are the uses of these designs or devices? Everything discussed here has its own application. Some we'll get to know in future in the next lesson. Some we do not discuss in the regular syllabus. Okay, but everything has a reason. Okay, all of them has got their own application, and now we are discussing the basic theory of that. So, the intention would be, again we have one more derivation to get the magnetic field inside the solenoid. Okay, the direction of magnetic field set inside the solenoid would be in a circular path like this, a closed path. Okay, this is how magnetic field lines look like inside the solenoid, like this, because when it is in a straight line, the magnetic field lines were straight. I bent it to form a circle or a ring, so it is completely like this. The magnetic field lines are parallel to each other and inside the toroid like this. So a solenoid bent in the form of a ring itself is a toroid, right? So now, uh, once again, our intention would be to get the magnetic field inside the toroid, similar to what we did with the solenoid. This time I'll leave the challenge to you. Okay, it's in the book. You can refer to it. Again, there is no derivation of it, but you have to apply the Ampere circular law itself, considering an Amperian loop inside the toroid. Okay, you should consider an Amperian loop inside the toroid and should get the total current inside the toroid. You can consider, let n be the total number of turns, and hence the total current would be Ni, total number of turns into total number of coil, because see, at every point inside the current would be either will flow into it or will come out of it. So since the Amperian loop now has a certain set of positive current, or a certain set of current Ni inside the loop, okay, this current will give the magnetic field, which is B dot dl is equal to mu naught Ni, where N is the number of turns, I is the current through each turn, capital N is total number of turns. Okay, and magnetic field is constant. I can take that out. What is left inside is integral of dl. So if I integrate all the dl's in the Amperian loop that I choose, which is equal to the circumference of the circle, so it is B into 2 pi r is equal to mu naught Ni. What is Ni? Total number of turns is number of turns per unit length into the total length or the circumference. What is that? 2 pi r again. Following? number of turns per unit length into the total length. The length is 2 pi r into I. So 2 pi r cancels, and will be again left with B is equal to mu naught Ni. So even for a toroid, the total magnetic field inside it is given by B is equal to mu naught Ni, where small n is the number of turns per unit length, I is the current through each turn, and mu naught is permeability of free space. Okay. So now even for the solenoid and toroid, this thing shall be kept in mind. Mu naught is taken only when the solenoid or the toroid has either vacuum or air inside it. If the space inside the solenoid or the toroid is filled with certain medium, then we should take the permeability of that medium and put that here. Instead of mu naught, we should go to mu there. Clear? So that is about, this is about toroid. Okay. Then few technical points about toroid is, one can ask what is the magnetic field in the empty region of the toroid, okay, which means inside the toroid is this part, okay, inside the ring or this region, okay. If they intend you to ask a question like that, okay, let me read the question itself. So the question says, what is the magnetic field in the space interior of the toroid? Okay, in the space interior of the toroid, in this region, the magnetic field here is 0 inside the space interior of the toroid. Even when you go out of the toroid, there also the magnetic field is 0. Okay. So this makes sense because if I take an Amperian loop here, okay, if I take an Amperian loop in this region, this Amperian loop does not have any current, right? There is no current inside the Amperian loop considered here. So I is 0 and hence B must be 0. That is why B becomes 0 in this region, the inside region. When I take it outside, okay, outside the toroid and take an Amperian loop, this Amperian loop has got current inside it, but look at the current here and here, they are exactly opposite. So we have as many currents in one direction equal to as many currents in the opposite direction, right? See, we have so many turns here, each turn has current going into the board, and here the same number of turns, each turn having the current coming out of the board. So it is somewhat like the total current is then given by plus Ni, okay, the total current. It would be like mu naught Ni, no? So integral of B dot dl is equal to, when I apply it outside the toroid, I am taking an Amperian loop outside the toroid and applying it. It is mu naught times, see, plus Ni for certain current, and since the direction of current has become opposite, I should consider minus Ni, and hence plus Ni minus Ni cancels, again 0. So B is 0 even when I consider a point outside the toroid. Okay. So this is very important. In the the empty space, the internal space of the toroid, this magnetic field is 0. Inside the coil of the toroid, okay, inside the coil of the toroid, magnetic field is mu naught Ni, and outside the toroid, the magnetic field is again 0. Okay. So these points are important. What is the magnetic field at different points chosen? Okay. So this is about toroid. And for both solenoid and toroid, you can see that they are dependent on these factors: number of turns per unit length and current. If I have more number of turns per unit length, which means, see, this has certain number of turns per unit length. Now if I compress it, now the number of turns per unit length is more when I compare to this kind of solenoid, because it is freely distributed, the turns are freely distributed, and hence if I take 1 meter of them, I can get something. But if I pack them closely like this, if I move them like this, now I have the same number of turns in a small length. That makes number of turns per unit length more for this kind of arrangement. So number of turns per unit length gives us more magnetic field, more the current, more the magnetic field. This is about both solenoid and toroid, because both of them has got the same expression for magnetic field inside them. Okay, so this is about solenoid and toroid. And one more graphical representation left. See, when I have a solenoid, okay, like this. See, I've told you that the magnetic field inside the solenoid is always maximum and constant, right? So, if I plot a graph for the magnetic field due to this solenoid in the along certain axis over the length of the solenoid. So, let me start from the center. At the center I can have maximum magnetic field, but as I move away, yes, since I am still staying inside the solenoid, the magnetic field is constant till certain point. But as and soon I approach the end of the solenoid, it decreases. Okay, it decreases to half of its value like this. Decreases to half of its value, and then moving ahead, it starts to decrease more and more and more, moving away from the solenoid, which means maximum magnetic field, maximum, 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 maximum. And now here the magnetic field is weaker compared to this, still weaker, 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 at infinity 0. Again, weaker, weaker, still weaker, at infinity 0 again. Okay, so this is what is magnetic field represented for the as a factor of length of as a factor dependent on the length of the solenoid. So, magnetic field, and this is the length of the solenoid. Okay, so this is maximum, which is BC, magnetic field at the center of the solenoid. Okay, this is a graphical representation. Fine.